Good afternoon, everyone. We will wait for 2 more minutes to start the class.
Good afternoon, ma'am.
Good afternoon, ma'am.
Good afternoon.
Okay, am I audible to you all?
Yes, ma'am.
Yes, ma'am.
Fine. So in the last class, we have completed the most important electronic effects that happen in an organic molecule. We discussed electromeric effect. We discussed hyperconjugation, isn't it? And we also discussed steric influence, though we didn't elaborate it, but still we saw steric influence. Today, we will start with the next effect that is most quite common in an organic molecule, which is called as either mesomeric effect or resonance effect. So what is the basic condition for a mesomeric effect? If a molecule has to show mesomeric effect, what is the basic condition? Look at this. The molecule should have a conjugated system. Sigma pi bonds should be alternative in position. Look at here in benzene. In benzene, how do we have? I have sigma here. 1 minute. What do you have in benzene? We have sigma and pi over here. Can you all see this? We have sigma and pi. Look at the next molecule, carboxylic acid, which is attached to benzene, which is nothing but benzoic acid we have. In benzoic acid, again, I'm able to find sigma bonds and pi bonds that are in conjugation. Can you see C double bond O, which is pi? Then I have C that is connected to the carbon of the benzene. Again, I have a double bond in benzene. So I have sigma pi conjugation is here. Look at the third case, where I have ethynyl chloride, where I have a pi bond, a sigma bond, where chlorine is having pi electron cloud. So in these cases, whenever you have this kind of a conjugation that could happen, then these kind of molecules will show mesomeric effect. These kind of molecules will show mesomeric effect. Okay. So now what is the difference between, first of all, this mesomeric? Okay, ma'am, if you say that sigma pi conjugation is happening, that is for the same thing that we learned in hyperconjugation also. It is also sigma pi conjugation. In hyperconjugation, the sigma of CH electron is being transferred is what we found. That means an hydrogen shift is always happening in an hyperconjugation, isn't it, everyone? Do you remember hyperconjugation or not? So, but here, that is not the case. Here, it is only about the electronic shifts. The shift is only about the electron, not the atomic shift like hydrogen that is happening. So, this is a permanent polarization of the group that is attached to the conjugated system. So, whatever group is attached to the conjugated system, there is always a permanent polarization that happens here. We all know what is polarization. Polarization is nothing but distribution of charges. That means partial charge that exists within the same molecule. So look at this molecule, NH2. What do I find here? In NH2,
can you repeat this mesomeric effect?
I am totally not able to hear you, man. Be louder, please.
Can you repeat this effect again?
Is there some mistake in my speaker? Louder, a bit louder, please.
Ma'am, he's asking you to repeat this effect, ma'am.
Mesomeric effect. Am I correct?
Yes, ma'am.
Yeah, okay. See, look at this molecule. 1 minute, I'll take better Word document. This is not allowing me to write anything on this. I hope you are able to see the screen now. The mesomeric effect is one which is going to tell us about the kind of conjugation that is happening between. What's happening? Why I'm not allowed? 1 minute. I'm not allowed to use my pen at all right now. Why? It's only showing only rubber simply. Oh God. One minute. Okay, here you're able to see sigma pi conjugation is happening. Similarly, look at benzoic acid. You have sigma here, here you have sigma, here I have pi, a double bond is there. Again, look over here, I have pi. So this kind of conjugation leads to polarization of charges. That means distribution of separation of charges. Look at this case. Here you have pi, here you have sigma. Here once again you have lone pair of electrons that is available on chlorine, again pi. So this kind of thing leads to a permanent polarization of the group that is attached to the conjugated system. This we will call it as mesomeric effect. Is it clear now?
Yes, ma'am.
Okay. So this is going to be a permanent polarization that happens. I told you what I was discussing was, how is it different from hyperconjugation? If people we have it in our mind. If I talk about sigma pi conjugation, it is hyperconjugation, isn't it? Sigma pi conjugation that happened in hyperconjugation involved alpha hydrogen in it. That means there was an hydrogen shift that was happening, isn't it? Hydrogen broke from its place, cleaved from its place, left a lone pair of electron there. That came on foreign conjugation. But here it is not about any atomic shifts and all. It is only about the pi electron cloud shift is happening. Look at this example. I have NH2. I have lone pair of electron on NH2. This is going on for the shift, where I am able to find a polarization that has happened here. Plus on nitrogen and minus on the carbon. Okay, so this kind of shift is called as mesomeric effect. So it means it's only about the electronic shifts. Only electron is shifting here. There is no hydrogen shift that is happening. Understood? Copy down. Okay. So, ma'am, in our textbooks, we have seen mesomeric effect bar resonance effect. So, are these both the same? They are same, but mesomeric effect is the one which you are able to see in this example, where this shift has given one kind of a structure. Is this a Lewis dot kind of a structure? Yes, whenever you are able to see some kind of charge disproportions that has happened in a molecule, we'll say it is LDS, Lewis dot structures they are. So if one of these structure is enough to make you understand this molecule, what is the next way of shift that could happen here once again? It is nothing but like this, isn't it? So in a way, only two structures are available for this molecule. So here mesomeric effect will be addressed. This effect that is shown by this molecule will be said as it is exhibiting a mesomeric effect. But there are certain molecules. For certain molecules, just one Lewis dot structure is not enough. You need to keep drawing so many structures. So with the multiple structures that can be drawn, if I need multiple structures to address one single molecule, just like a benzene, Kekule drew actually 66 forms of benzene, actually, resonance hybrids of benzene. So if you have multiple structures that has to be written in order to make you understand, then that is called as resonance. That structure is called as resonance structure. Those structures will be called as canonical structure, and that effect will be called as resonance effect. So in generally textbooks, they will tell you mesomeric or resonance effect. Mesomeric is correct when just one Lewis dot structure interconventions is possible in order to understand the migrations of the electron, then it is mesomeric. If you need so many structures in order to understand it, we call this as resonance structure or canonical structures. Both the words are the same, and that effect will be called as resonance effect. Okay. So what do you mean by this plus
Ma'am, one
M
minute, ma'am, I
effect.
didn't copy.
Okay, okay.
Ma'am, this is all in the Google Drive.
All are in the Google Drive. What I'm telling you now is from Google Drive notes only. The next scroll down.
Ma'am.
And the next thing that we generally look in your chemistry textbooks is that where it is shown as plus R effect, plus M effect, minus R effect, or minus M effect. Is it something that is in relevance with your plus I effect and minus I effect? So generally children get confused in this aspect. So let us see. It is usual that when I say plus I effect, whenever I say plus I effect, what do you understand? The group that is attached, isn't it? The substituent group is an electron donating group. When I say it is minus I effect, what do we understand? The substituent group is an electron withdrawing group. This we know it already, isn't it? Then what relevance does it have with this plus M effect or the plus R effect? What does it mean? Whenever this group is an electron donating group, also it is involved in resonance, then we call such effect as plus M effect or plus R effect. And what do I mean by resonance? See, for the example of phenol, we will be learning a new reference in full now. Phenol, I have the lone pair of electrons on the oxygen. Once it is losing its H, we already studied phenoxide ion. I hope you remember phenoxide ion, isn't it? So now what happens? Because of this lone pair tendency, as well as this negative formal charge, there is a shift that is happening here. So this is involved in resonance as well. This lone pair is involved in the resonance as well. Its electron is involved in the resonance as well. Then that kind of groups will be showing plus M effect or plus R effect. Look at here. I have phenol, where I have the OH, I have the lone pair of electron, isn't it? Again here, NH2, amines. We have the lone pair of electron OR. Again, I have lone pair of electron NR2. Again, I have lone pair of electron NHR. I have lone pair thiol. I have lone pair, isn't it? So all of them will be showing a plus R or plus M effect whenever they are involved in the resonance. Then they will be called as the group which show you a plus or effect. All right. Okay, ma'am. So what about bromine? Let us take the halogen for this case. And halogens also have their lone pairs. See, I have still their pairs of electrons are available. But let me start shifting it for your conjugation as per mesomeric or resonance effect. Once it is done, what is happening? Bromine gets a positive charge. Bromine is already an electronegative group, isn't it? It's an halogen. Halogens, we know they are very good electron acceptors, electron withdrawers. So therefore, a positive charge in the bromine is not acceptable. It is least reactive. So whenever people address plus M effect or plus R effect, they are induced by these groups technically. Could be an hydroxy, OH, amine, oxy, that means methoxy or ethoxy like OR, NR2. All you can see is the substituted amines here, primary, secondary, and tertiary amines, and you have thiolic groups here. Okay, so all of them would give you plus M effect. So what is this plus M effect?
Ma'am, here it's written electron donating group show plus M effect, ma'am.
Yes,
We
yes.
explain how bromine, but bromine is, you just said bromine is an electron accepting group. So,
That's what I say. Even why I am taking this example is that even in this place, I am able to see lone pair of electron is available on bromine. Yes or no in this example? So if there is a chance for it to go for an mesomeric effect, bromine would get a positive charge. So this is not allowed actually. That's what we are telling. Why I am choosing this example is that all of the examples I'm showing you lone pair of electrons. So even if it is having LPA, it will not be able to do a plus M effect or plus or effect because it becomes positive.
Okay, ma'am.
That is not acceptable. Okay.
Okay.
Now, what will this plus M effect do for a benzene? We will be learning resonance in a very short time. Plus M effect generally activates the benzene ring. Activating means benzene is becoming very active towards electrophilic substitution reaction. Electrophilic substitution reaction, benzene is becoming activated whenever you have these groups. And this electrophilic substitution happens at ortho-para position. Electrophilic substitution really gets activated at ortho-para position. What about this minus M effect? Minus M effect deactivates the benzene ring. That means whatever if the electrophile is coming and attacking the benzene, what happens? What is minus M? Minus M is the one, if plus M is done by electron donating group, minus M will be done by electron withdrawing group. Look at this example. Minus M effect is opposite to plus M. Here, what is happening? This group that is present here is trying to pull the electron towards it. But what happened here? Whenever you have an aniline, let it be an NH2 that is present on the benzene with lone pair of electron, that shifts its electron towards benzene. But here, what is happening? The group that is present is pulling its pulling the electron from the pi bonds. So this is minus M effect. So if this minus M is present on a benzene ring, let us consider if a ketonic group or an aldehyde group, benzaldehyde is there, COH is there, they are quite electron withdrawing. So what they do, they start pulling the electron towards them from benzene. Okay. So in those cases, we call them as minus M effect. In such cases, generally this electrophilic substitution reactions happens at a very low rate. It is not allowed. What is the reason? What is an electrophile? Electrophile is the one which is in need of electron. So if this group which is present on the benzene is pulling the electron from benzene, then how will the electrophile get attracted to the benzene? Benzene is not having pi electron density there. So therefore, minus ML effect will deactivate the benzene ring. Okay. So if an electrophile is going to come over here, I will take up this point when we are discussing some other things. So right now, you just write this. Plus M effect activates the benzene ring. That means benzene is quite available for electrophilic substitution. Minus M effect deactivates the benzene ring. So that means the electrophilic substitution reaction is not favorable there right now. All right. Now look at the second example, B. This is aniline, isn't it? Benzene that is attached with NH2, aniline. NH2 is having lone pair of electron. Therefore, plus M effect is shown. What is plus M effect? It is an electron donating group. Also, it is getting involved in benzene. I repeat once again, it is an electron donating group. Also, it is getting involved in resonance. So that is called plus M effect. So generally, this question is very common. The question is, which is a weaker base? Which is a weaker base? Whether aniline or a methylamine? Which is a weaker base? See here, the lone pair on nitrogen that is available is not taken by R. R itself is a electron donating group, isn't it? So R, what does it do? It just keeps moving, shifts its electron towards N. So therefore, I mean, the lone pair that is present over here, it is a very appearing to be a very strong base. But what happens in an aniline? What happened in aniline? I had NH2 here, but what's happening? This is involved in resonance. So the lone pair is right now not available for basicity. So therefore, aniline is a weaker base when you compare to common alkyl amines. Is that clear?
And since
Is it clear?
like a benzene ring is electron accepting like that, no.
Yes, yes. Benzene itself, phenyl group itself is an electron withdrawing group, isn't it? So much of pi electron cloud is there. So in order to stabilize itself, it just seeks its electron density. Look at the third example. You have an halobenzene and you have alkyl halide, which is less reactive. Here, we know halogen itself is an electron withdrawing group. It itself needs an electron withdrawing nature. So if it is really electron withdrawing, the half should be in a position to donate the electron to X so that it is becoming active enough. But here, what is happening? Benzene, compared to X, benzene is more electron withdrawing because of its 3 pi bonds that is available there. So therefore, X is made to donate the electron. Here in this case, you can see bromine is made to donate the electron for one single bond. Here in benzene, your 3 double bonds are there. So the X is there in the position to donate its electron to these 3 pi bonds. So therefore, this becomes less reactive compared to your alkyl halides. We will be learning about so many organic chemical reactions where this trend is noticed. When I take some chloromethane or methyl chloride reacted with sodium hydroxide, it will be there will be direct nucleophilic substitution reaction giving you methanol. But that doesn't happen in a halogenated compound. It's very difficult. Copy down. So what are the things that you have to copy down from this is plus R or plus M effect, the group that is phenomenally showing the effect. These 3 case studies, A, B, C, and this box.
Ma'am, for the second case study, can you explain why the benzene ring is less basic than
See, when you say weaker base, it means it does not have much of electron density on it. We should have studied Lewis acid and Lewis base, isn't it?
Yes,
So a
ma'am.
base is the one which donates electron, Lewis acid is the one which accepts electron. The lone pair that is present on the nitrogen, if it is still available on nitrogen, then it will be a very good Lewis base. Considering aniline and a common alkyl amine, we know alkyls they themselves are electron donating groups. So they start shifting their electron cloud towards this nitrogen. So now the nitrogen is full of electrons. Already it has a lone pair of electron. Also the electron cloud from R is also approaching nitrogen. So it is a good base, isn't it? It is a good base compared to aniline. But in the case of aniline, what happens? The lone pair of electron on nitrogen is getting shifted towards benzene because benzene is an electron withdrawing group. Since the nitrogen itself does not have its lone pair density on it, so it will be a weaker base.
Okay, ma'am.
Maybe I think you are confused with the word weak base and that arrow mark there. Huh? I just give the heading as basicity.
Ma'am,
Hmm.
in spite of acquiring a positive charge, that bromine is bromine also an electron donating group?
Yes, yes.
Yes.
Roman will be showing you minus I effect. There is no doubt about it. Okay. But
Okay, ma'am.
when it is present in a pi electronic cloud, whenever it is present in a pi electronic cloud, this has a tendency to give out its electron, like plus M effect or plus R effect.
Yes, ma'am.
Over? Okay. So the discussion that is given down is once again what we discussed now. So the group which can donate electron to the benzene ring as well as participate in the ring conjugation resonance effects will be called as will be giving you plus M or plus R effect. If they can't participate in ring conjugation, ma'am, they are not participating in ring conjugation and all, but still they are able to provide, but still they can increase the electron density on the benzene ring by induction. That they are able to do. Okay, that they are able to do. Then that kind of group is what we call it as plus I effect. I repeat once again, what is the difference between plus I and plus R? Plus R means they will be getting involved in resonance also within the benzene. Plus I, it means it is just having the possibility of donating the electrons to the benzene ring, but they do not get involved in the resonance and all. So what is the main clue point here? Whenever you see the group is having lone pair of electrons, then they have the possibility of showing this plus M and plus R. Look at the example of plus I. It is just ethyl and methyl. Ethyl and methyl do not have the lone pair, isn't it? So they have no ability to get involved in the benzene's resonance pattern. Similarly, if the groups withdraw electron from the benzene ring, as well as it disturbs the resonance, ma'am, it is just now we saw minus M deactivates the benzene ring. So it's a deactivator of resonance. Then they are called as minus M and minus R effects. Okay. So here you are able to see C double bond O, COOH, carboxylate, cyanide, nitro, whichever is having. So many are coming very late. Okay. So whenever they have a stronger way of withdrawing the electron from the benzene, so that the benzene's resonance is disturbed there, they will be deactivating the benzene ring. Out this, I would like to say something about halogens, a specific thing about halogens. Halogens groups, generally we know they are electron withdrawing in nature. So they have a minus I effect. They show a minus I effect. But also, what they do is that in the presence of benzene, because benzene is becoming having 3 double bonds there, more electron withdrawing than halogen itself, it, as we saw just if it is a bromobenzene, assume it is a bromobenzene. So what happens is that the lone pair of electron that this bromine is having is continuously being pulled by this benzene, so which is getting involved in the resonance. So it is showing a plus R effect. Even though it is minus I, in the presence of benzene, halogens will be showing plus R effect. Now, what is the main thing that we should understand about this plus R and minus M effect and all? See, we will be with respect to benzenes. Benzene electrophilic substitution reactions, generally they happen at 3 positions, isn't it? We already have discussed in IUPAC nomenclature. When I say benzene, let it be some Z. This is ortho, this is meta, and these 2 positions are para. So an electrophilic substitution reaction may happen at any of these sites. If it is a plus I effect, the group is showing plus I effect. Then the electrophilic substitution reactions, not substitution, sorry, addition, electrophilic addition reaction, EAS, will be happening at ortho and para position. If it is minus I effect, then electrophilic addition reaction will have meta position. But there is an exception here. The exception is with respect to halogens. Halogens show minus I effect, but still they show the EAS at ortho para position only. Okay, this is based on resonance. I repeat once again, Those groups which show the plus I effect will go for electrophilic addition reactions at orthopara position. So it is not that the resonance at plus R minus R is not dictating you the groups, the substituent groups, incoming groups position, which is dictating. If it is a plus I effect, if the substituent that is present here is showing a plus I effect, then the EAS will happen at OP. If it is showing a minus I effect, the EAS will happen at meta. That is the exception. If it is an halogen, halogen is having minus I, but still it happens at orthopara position only. Just now we discussed it is showing plus or effect, isn't it?
No.
Is that clear till this? Yes. Did someone
Yes,
say
ma'am.
something? Yes, tell me. No, was it a question or you're affirming yes, you understood? What was it?
Ma'am, I said I understood.
You understood, okay. Copy down. And say attendance, Mohit,
Present, ma'am.
Ravichandran, Sharan,
Present, ma'am.
Nitish,
Present, ma'am.
Abdul Basit, Surya,
Yes, ma'am.
Shreya, Shreya is here. I saw coming in. Yeah, she's here. Govardhan, Rohan, Rohan, Shreyas,
Listen, ma'am.
Manish,
Present, ma'am.
Tarun,
Yes, ma'am. Present, ma'am.
Sunanda, Sunanda, Kumaran, Harichandran,
Present, ma'am.
Nishita,
Present, ma'am.
Naveen, Shika,
Present, ma'am.
Krish, Krish is here. Oh, Syed,
Present, ma'am.
Aditya,
Yes, ma'am.
Sri Raksha, Sri Raksha, Jacob, okay. So just we have learned about the mesomeric effects, plus M effect and minus R effect or whatever it is. So how is it getting understood? That is what we have learned till now. So the most common question that we could expect from this mesomeric effect is that people will be questioning us about the resonance, which is the, tell me,
Ma'am, you haven't called my name yet for attendance.
what's your
Mom,
name,
you
da?
haven't called my name as well.
No, I think you're the new students, or either you should have changed your batch, correct?
Yes, ma'am.
Yeah, still they haven't joined your names in the attendance.
Okay, ma'am.
Fine. So, what is the most common question that we could expect is that the question is about the resonance structures. What is resonance and what kind of structures are stable enough? So that we will see now. What are the conditions to draw the resonance? So when I say resonance, as I told you, resonance is nothing but mesomeric means one shift is enough to understand the structure or what is the way the shift can go on. But ma'am, one Lewis dot structure is not enough. I need so many. There are so many structures which can put together resemble this one single structure. Then that kind of thing is called resonance. Now, why is it generally done? We know that any molecule in chemistry or even anything in universe wants to be at rest. That means it should have least energy. So many are the structures that are compiled. The total energy is being equally distributed among these structures. So their potential energy level goes down. They become more stable. So what we are learning now is resonance. So the possibility of many LDS, Lewis dot structures, leads to the delocalization of electrons. So many electrons are there. Electronic cloud is getting delocalized. Ma'am, what do you mean by this delocalization? Delocalization means it is stationed at one single site. Delocalization means the electronic cloud is on a continuous move. It's continuously moving. It's not at one single place. That is called delocalization. Okay. So the energy is becoming less, therefore it becomes more stable. This was what you call as canonical structures or resonance hybrids. So many structures are there. Out of them, what do I mean by a canonical structure? The most stable resonance hybrid, acceptable structure or real molecule is a hybrid of all these structures. So generally, if I'm going to say, ma'am, this is the resonance hybrid, that means so many structures, ma'am, I just keep shifting the electrons throughout this ring or throughout this molecule. And at one single place, I am able to see they look more or less the similar. They look more or less the similar. Then in that positions, then I call them as resonance hybrid. That is how I start showing the real molecule as well. Okay. So see, for example, if I'm going to show you like this. Aren't they the same? I can exhibit both of them and both of them are same. And I can also say this is also the same. Because I understand that this pi electron cloud just keeps on delocalizing throughout this molecule. So generally benzene is shown like this, isn't it? So look at these two structures given here, 1 and 2. The position of double bonds is still alternative only. If I count the number, still it's going to be the 1, 3, 5 or 2, 4, 6. It's going to be more or less the similar. The energy that is taken by these molecules are the same. So now not used as pi electron is not seen. Continuous cyclic triene is still conjugate here. So what do? I just give you a cyclic ring inside it. It is a continuous cyclic triene is present, isn't it? At the alternative positions. So these two structures are energetically in equivalent form. When you take up the energies of these two molecules, both are same only. They are not much different. So therefore, they become the resonance hybrid. With this resonance hybrid, we show the molecule of benzene structure like this. Now in chemistry, we generally don't just keep doing all the structures. So what do? We use either of these two resonance hybrids. Either this or this. I could even draw this. I can even draw this. Both are same. Understanding that one of this structure is not going to completely define benzene. I know that. If I draw this, and start doing some reaction, I know that this is not the only structure which is going to explain the overall reactivity of benzene. The overall reactivity of the benzene, this is not going to say. I know that. Knowing that only for proper understanding and to make the concepts simpler and easier, we use either of these three forms. Okay. And this is the reason why benzene is highly chemical stability, high degree of unsaturation, is puzzled. And whatever benzene and its related compounds you take, ma'am, it could be an allobenzene, some alkyl benzene, anything, they are highly chemically stable. And they have a high degree of unsaturation as well. That remains a puzzle. Why only this is having? See, for example, I have this molecule. And when I compare this molecule, I can see this. Let me say this is a molecule and I see this molecule. I can see this is very stable. This is very stable and it has a higher degree of unsaturation as well. And what makes it to be very stable is the question. What made this to be very stable? Is this because of it is having 3 bonds? What if the 3 bonds are going to be in a continuous way, like allenes? You have seen it, right? In allenes, they are continuous. Won't they be having that kind of a stability? All these things are explained by resonance. All these things are explained by resonance. Okay, you need not copy all these stuffs. I'll tell you what to copy, okay? Now, when you take the benzene, this you need to copy. When you take benzene, when you see this carbon-carbon bond length, it's 139 picometer. It's identical. All the carbons there, CC, is 139 picometer. But this 139 picometer is nowhere relevant with what carbon is present there. See, I know if I say benzene is there, I have single bonds as well as double bond. I can see this 139 picometer is somewhere in between the carbon-carbon double bond distance as well as carbon-carbon single bond distance. Bond length of double bond is 134 picometer, while a single bond is 154 picometer. But what I have right now is somewhere in between these two values. So we can understand some kind of overlap has happened between this carbon, which has led to this kind of an in-between value. And there is a reason why they have identical bond length. How amazing is this? They have an identical bond length, even though they have double bonds at place and single bonds at place. As you see, they are having identical bond length. So what does it mean? It means the pi electron is not localized. It is not just present here. It is not just present here. It is not just present here. It is actually present throughout. That is what it means. Okay. You need to copy this one. So going on with respect to the resonance energy. You look at resonance energy. So what do we understand? See, if it is 139 picometer, it is not actually made of only about C double bond. See, it is not actually made up of only CC and C. So what is made of? So scientists claim that, okay, the resonance hybrid of benzene, which you said is the most stable form, this maybe would have made up of 1.5 times of CC bonds are there. And that is the reason why you have this kind of a bond length. Okay. So the carbon in the benzene ring is sp2 hybridized. We know that. Yes or no? It is sp2 hybridized. So now when I look at this, when I look at the bond angle, it is 120 degree, which makes it overall planar. That means they are completely planar molecule. Just like this. There is no in and outs of the in the plane, out of the plane. There is nothing like that. They are completely in overall planar. So people generally, how do they define benzene? Planar, cyclic, conjugated, 4n plus 2 pi electron. All these things, delocalized. All these things are the right words to explain benzene. Okay. So with respect to your bond energies, what is benzene? Benzene is nothing but, what is benzene actually? Benzene is nothing but if I have a cyclohexane, when I'm going to remove 3 hydrogens out of it, it becomes benzene, isn't it? It becomes benzene. So it is nothing but hydrogenation of benzene will give you cyclohexane. We can take it in that way also. So when people compared the bond energy of the benzene, So this is cyclohexane, which is said to be having the lowest energy, assuming this line is lowest energy. So let me start with cyclohexene. This is cyclohexene. When I hydrogenated, the bond energy is 28.6 kilocalorie per mole. Hydrogenation, enthalpy of hydrogenation. We have learned it already in thermochemistry. If it is cyclohexadiene, the enthalpy of hydrogenation should be 2 times of it. If it is cyclohexatriene, hypothetical form, hypothetically you can see it is not actually planar molecule, not like our benzene, usual benzene. It is just having some kind of a canonical structure. Hypothetical cyclohexatriene, 3 double bonds, so it should be 28.6 multiplied by 3. So hypothetical cyclohexatriene should have 28.6 multiplied by 3 times of bond energy, degree of hydrogenation or enthalpy of hydrogenation, isn't it? This much amount of energy it should have. But actually, how much benzene is having? Benzene has just 36 kilocalorie per mole, which is in between cyclohexene and cyclohexadiene. Lower is the energy, more is the stability. Even though it is having 3 double bonds, how much is the energy? It is in between cyclohexene and cyclohexadiene. So lower energy actually. That makes benzene very stable. So what makes this benzene very stable? This delocalization. This conjugative double bonds and delocalization makes benzene very stable. Okay. Copy the diagram as well as this point. This and this. If I arrange for some class in this week online, will you be able to attend it?
This week not possible.
Not possible. What about some, like after 8 o'clock, something like that, possible?
Yes, ma'am.
Not, but would it be difficult for you after attending school, again sitting for a class by 8 o'clock at night?
No, ma'am.
No? Okay. Okay.
Ma'am, 28.6 into 3 is the enthalpy for hydrogenation, right, ma'am?
Hydrogenation of cyclohexatriene.
Okay, ma'am.
Yeah. Benzene is also cyclohexatriene. Na? So hypothetically,
Yes, ma'am.
if it is a 1 bond, if it needs 28.6, if it is a double bond, it may require 2 times of it. And if it is a 3 double bonds, it should
Okay.
require 3 times of it. But benzene is not like that. Benzene requires only 36.
Okay, ma'am.
What up? Not going into much chemistry concepts of resonance, I would like to. So what really happens is that carbon, we know it is having 1s to 2s to 2p2 configuration. With its hybridization mode, we expect it to be sp3, where sp2 we know it is sp2 hybridized, isn't it? So 1p is still unhybridized in carbon of benzene, so which is perpendicular to the plane of the ring. Can you see this? They are perpendicular to the plane of the ring, where they go for some molecular orbital forms. So by this overlap, they form 6 molecular orbitals. One is 3 bonding orbitals, another is 3 anti-bonding orbitals. This is what leads to the resonance energy of benzene. So what should we understand about this is that what gives the resonance energy for benzene? It is a formation of molecular orbitals, 3 bonding and 3 anti-bonding, and these p orbitals are perpendicular to the plane of the ring. So now if you look at this, it is 36. 36 is its resonance energy, okay? The energy that is possessed or that is exhibited by a molecule when it is showing resonance, that is called resonance energy. I repeat once again, the energy that is exhibited by the molecule when it is exhibiting resonance. Ma'am, what is resonance? Resonance is nothing but a continuous shifts of electron that happens, delocalization. Okay, so you can see this. Tell me, ma.
Can we find resonance energy?
Can we?
Calculate resonance energy.
We have actually in thermochemistry with this bond energies, we will calculate resonance energy. We can. I have also sent you the thermodynamics, thermochemistry question paper that you have solved. There,
Okay.
the resonance energy is there. Okay, with thermochemistry calculations, we can calculate. Naphthalene, look at the resonance energy is 61. Cyclopentadiene, 3 is its resonance energy. Butadiene, 4 is its resonance energy. Look at the resonance energy difference. Butadiene and benzene. What makes benzene to have this much of energy compared to butadiene or compared to cyclopentadiene? The reason is that more resonance structures can be drawn with respect to benzene. So more are the resonance structures, the more will be the energy that is exhibited by the molecule in the form of resonance. Okay. So let us go for the resonance conditions. Right. So 1 minute, I take up the conditions. Very important. Conditions for resonance structures. So mostly I think you should have seen your question papers filled with resonance structures in your school exams as well. Right? Okay. So what are the rules for resonating structures? For which kind of structure can I draw a resonating structure? You will be able to draw the resonating structures only for a molecule with more than 1 double bond or triple bond. You will be able to draw the resonating structures only for a molecule with more than 1 double bond or triple bond. Now, first condition, more should be the covalent bond. I know whenever you start counting the bonds, they are covalent bonds. Even a sigma bond is a covalent bond. Pi bond is also a covalent bond. So if your resonance structure is having more covalent bonds, then that is stable. If it is a neutral molecule, they are stable. The first two conditions, they should have, if they have more covalent bonds, and if they are more neutral, they are very stable. Second condition, the charge should be conserved. What do I mean? What do you mean? Ma'am, when I start shifting the bonds, first structure is having 1 negative bond, ma'am. The second structure is having two negative charges. Not possible. The total number of charges shown in all resonating structures should be the constant. They should be constant. What does it mean? It means that if you're going to draw the resonating structure, how will it be? It should have continuous same number of charges only, not different. So that is very important. The next one.
Ma'am, can you give an example?
See, for example, if I'm going to draw one, like and you will be seeing structures now. If this is a phenoxide ion, how many negative charge it has right now? Minus 1, isn't it?
One.
So if there is a shift here, Yashwanta, what happened, Ra? Continuously you're coming out and going out. There is a shift here. Again, how many charges it has? Only 1 negative. So there should be conservation of charges should happen. If it had one negative, the same 1 negative should be there. If it had 1 positive, the same 1 positive should be there. If your resonance hybrid should not have different numbers of charges. That's what it means. Understood?
Yes, ma'am.
Okay. Going to the next one. Two opposite charges adjust to each other or unstable. CH2 minus is there, CH plus is there. When they are close together, they are unstable. More separative charges are stable. More separated are the charges, they are stable. Then, position of the atoms and their connectivity is constant. I repeat once again. Mesomeric or resonant effect is only about the shift of the pi electronic cloud. It is not about anything else. It is not about, ma'am, I moved hydrogen, I moved methyl group here and there. That is not allowed. Only your charge should be moving around. Next, valency of the respective element should be maintained. What does it mean? If carbon can have only 4, carbon can have only 4. By doing my resonance structuring, you cannot have more than that. That is not possible. Also, octet should be carbon. Any structure where carbon has no octet satisfied. It's not satisfied. It's not octet satisfied. Then it is unstable. Carbon didn't form bonds at all, ma'am. Carbon is having positive charge there. So carbonium ion, ma'am. Then that kind of structure is not stable. That kind of structure. So generally, what kind of questions you can expect? They will be giving you various structures, asking you to find out which is stable or find you the order and all. So you have to first look for, if it is having more covalent bond, it will be stable. If it is neutral, it will be stable. If they have satisfied their octet configuration, they will be stable. If the charges are far away apart, they will be stable. All right. In the list of the resonating structure, two same structures can't exist. I write the same structures.
If there's two rules, both supporting opposite cases, which rule takes preference?
See, the first one, neutral is always better than charged one. If a compound is neutral, that is more stable than the charged one. So if they are giving you 3 structures where one is neutral, the other one is having charges, the neutral is stable. Now, between these charges, if they are going to be in the same molecule, adjacent charges are there, far apart charges are there, then again, the rule comes in. Okay?
So in the same order itself, preference will be there.
Same order one, yes, correct.
Okay.
Next one, electron donating group can have positive. Electron withdrawing group. Tell me, ma.
Ma'am, so if there is structures like methyl carbocation, methyl carbon, methyl carbanion, and methyl which is possible. Methyl. I'm asking which is more stable.
Which one, ma?
Which is more stable one?
Which one? You didn't tell me at all.
Methyl carbocation, methyl carbanion, and methyl.
In the same structure or different structures you're asking?
Same structure. I mean, sorry, ma'am, different structures.
See, a carbon should have satisfied its covalency, I mean octet configuration. If it has not satisfied, then it will be less stable. Okay? Yashwanta, what happened? What's the problem? Is your internet so unstable? You're continuously getting in and out?
Among a carbocation and carbanion, which will be more stable in terms of resonance?
That's what I'm asking.
See, it is not about just a carbocation or a carbanion. Okay? If considering carbocation and carbanion has not satisfied its octet. So it will be lesser stable with respect to your carbanion configurations.
Okay.
Okay, 6th one. Presence of at least two equivalent resonance structures of molecule is resonance stable. It means, ma'am, they are equivalent. They are not exactly the same. Look at the fourth point. In the list of resonating structure, two same structures can't exist. That is not possible. See, for example, when I wrote benzene, I wrote like this. They are not same structure, but they are equivalently similar, isn't it? They are not same, but they are equivalently similar. So presence of at least two equivalent resonating structure in a molecule is resonance stable. That is the reason benzene is resonance stabilized. All right. So that is important. Is it clear?
Ma'am, can you explain the fifth point?
Okay. Electron donating groups can have positive. See, a carbon can have positive. See, when you write resonating structures, there can be 6 or 7 resonating structures. It is not that, ma'am, a carbon is having positive. So it is not possible. We can't say it is not possible. It is less stable. That's it. See, all these rules are telling you about which is less stable, which is more stable. That's it. So if a carbon is having positive, yes, it is okay. But electron withdrawing should have negative only. Chlorine cannot have positive. This makes it very unstable, isn't it? Yes or no? So this you have to look up at the structure. When you have a structure, you should ask whether it is stable or not. Look at it. If it's an electron donating group, it can have positive. A carbon can have positive, not a problem. But if it's an electron withdrawing group, electron negative group, okay, highly electronegative group, like it could be oxygen, it could be chlorine. If there is a positive charge on them, then that makes them unstable. Is that clear?
Yes, ma'am.
Yeah. Okay, so here you have acetic acid is present, which is stable and which is unstable. Look at this. This is one of the resonating structures we are able to see. There's a shift from here. So it is a C plus and O minus it is becoming. Okay. But here in the second case, H plus is released. So here it has become something like this. This is not resonating structure actually. Because resonating structure, you don't remove the ions from there. It's only the shift like this. What we are seeing right now. This can happen. But when you consider just an acetic acid and an acetate anion, when you compare both of them, which is more stable if you ask, consider here. You have positive on carbon and you have negative on oxygen, but the charges are so close with each other. So that makes them unstable. More energy they gain, so they become unstable. But look at this structure. Here you have negative on oxygen, that is allowed, and carbon also has satisfied its octet, so this is stable. That is the reason why acetic acid tends to give H plus to become acetate ion. Okay? Is that clear? Hello? Am I
Yes, ma'am.
audible? Fine. Then what else we can understand? For a compound that obeys 4n plus 2 pi electron, which is called as Akul rule. I think I already expressed in the class about this. That makes it aromatic. Due to delocalization of electron, resonance is getting stabilized. So for benzene, why it is getting resonance stabilized? Because it is still aromatic. There are few examples where the aromatic nature is very important for resonance stability. So if it is aromatic, then you can consider, yes, there is a possibility for it getting resonance stabilized. Look at this example to understand this. This molecule is called furan. A five-membered ring where oxygen is a heteroatom there. Is this resonance stabilized? Here you are able to see its lone pair of electron is within this ring and one lone pair is outside of the ring. So let me count the total number of electrons. 2 here, 2 here, 2 here. Totally how many electrons? 6 pi electron. Is it obeying 4n plus 2 pi electron? What should I get? When I substitute some number for n, I should get 6. Is that possible?
Yes,
If I
ma'am.
substitute any number. Let me
Yeah.
substitute n is equal to 1. We will get 6, isn't it? Yes. So therefore, furan is aromatic compound and it is resonance stabilized. Okay. So if it is an aromatic compound, delocalization of pi electron. Ma'am, is there a possibility of delocalization of pi electron here? Are they in conjugation? Are they in conjugation? Yeah, it is pi, sigma, pi, sigma, pi. There is a conjugation, isn't it? So delocalization is possible. Pi, sigma, pi. There is a delocalization that is possible. So therefore, furon is stabilized. Clear?
Ma'am, here the lone pair will be taken as a pi bond.
See, lone pair is nothing but a pi electronic cloud only. It does not introduce identity bonding. So you have to take it.
Okay, ma'am.
Look at here. This is pyridine. Pyridine, an organic, weak organic base it is. Look at the structure. The lone pair of electron of nitrogen is outside the ring. So it is not involved in resonance. But how many electrons I have? 2, 2, 2. So I have 6 pi electron. Is it resonance stabilized? Yes, it is resonance stabilized. Yes or no?
Yes,
Hello?
ma'am.
Yes, ma'am.
Yeah. Yes. So look at this case. So there are so many cases that I have given. I don't have time to go for all of this. Fine. Look at this structure. Benzene. Where aromatic compound delocalized, it's a resonance is stabilized. Look at this structure. Is it resonance stabilized? No, it is not resonance stabilized. Why? It is sigma. Sorry, it is pi here. It is sigma here. Again, it is sigma. There is no delocalization that is possible. Yes or no?
Yes,
Hello?
ma'am.
Yeah. So therefore, it is not resonance
Yes,
stabilized.
ma'am.
Okay. So these kind of questions are quite common with your stability of resonance. Okay. Resonance structures. See, these are from your archives. Which of the following is not a resonance structure of the other? So they will be providing you with one structure, asking you to find out which is not a resonance structure. So what should you do in those cases? Start shifting the electronic load. See, look here. I have a negative charge on this oxygen. So I start shifting it. I'm able to find a negative here. When I started shifting here, I ended my bond over here. So it's negative here. Initially it was 1 minus. Here also it is 1 minus. Again, I start shifting here. What do I get? When I start shifting here, where do I get the negative? I will get the negative here, isn't it? I'll get the negative here. So like that, it should be you have to keep on shifting and to find whether it is possible or not. The question was, they have given you 4 structures here, 1, 2, 3, and 4. They're asking you which is not a resonance structure. So when you start shifting your pi electronic cloud, you need to find whether it is possible. Yes, look at this case. Yes, it is possible. The B is possible when I shifted from this way to this way. C, whether C is possible. Look at here. Yes, when I shifted the pi electronic cloud from this way to this way, I'm able to find the negatives here. Yes, this is also possible. But whether this is possible, this was not possibility. Why? What is the reason? If I again went for a shift, look at this shift, pi from here to here and negative from here to here. Look at this. This molecule is possible. They have not given this molecule. Okay, let me go for the next shift. From here to here, from here to here. This is possible, but this is not possible. Okay, so that kind of questions are quite common. Look at this. The circle represents more basic atoms in this molecule. Most basic ones. Which of the following is the correct representation? So they have shown the nitrogen is here as well. The nitrogen is here as well. They have circled this nitrogen telling you this is resonance stabilized. Is it correct? Yes. Because its lone pair is outside only. So therefore it is resonance stabilized. Here. Look at the question. It is more basic atoms. More basic it is. The lone pair has not got introduced into this electronic cloud. It is still available. Yes, it is correct only. Look at here. This nitrogen is bonded with benzene. Direct connection with benzene. So it will be its electron will be continuously taken up by benzene. But what about this nitrogen? You have 2 ethyl groups that are added to it. Electron donating groups. So therefore it is basic. Correct. They have marked this nitrogen. It is basic only. Correct. Look at here. You have NH2 here, you have NH2 here, NH2 here, CN here, and they have circled NH2. Look at this NH2. It is bonded with carbonyl group, which is an electron withdrawing group. So it will not be basic. Look at this NH2. It is bonded with a double bond. It is a pi electron acceptor. So this will not be stable. I mean, this will not be basic. Look at cyanide. Cyanide is already, nitrogen is going for a coordinate covalent bond with carbon. So nitrogen's lone pair is already involved in bonding with carbon. So it is not basic. Look at amine here. It still has its lone pair of electron left out. So yes, it is basic. So all of them are basic here. Is it clear? Is that clear, ma?
Yes, ma'am.
Okay. So these kind of questions are very common. Now we will go on with resonance. So we need to spend some time with resonance. Now they are giving you certain set of conditions. They're asking you whether it is correct or incorrect. If it is incorrect, how it is incorrect. This is the first molecule that is given to you, acetamide. So acetamide, they say it is undergoing some resonance and you get this kind of a structure. Is it possible?
No, ma'am.
Will you get no? Why?
And because atom arrangement is not the same.
Exactly. Here you are able to see that hydrogen is being attached to oxygen. So no atom displacement or no atom migration is possible. So this is incorrect. Look at the next one. They are showing you the curves also, telling you this. Telling you the oxygen, the bond, pi bond from oxygen is getting shifted over there and it is forming this structure. It is correct. Is it correct? Again, it is incorrect, isn't it? If oxygen is donating, it will not take a negative charge. Not possible. Yeah. And if it is given to nitrogen, count the number of electrons right now nitrogen has. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Is it possible? It breaks octet, isn't it? So it is incorrect. Do you understand this?
Yes, ma'am.
Yeah, look at the next third one. Again, they say the oxygen is shifting its bond towards this side and oxygen is giving a double bond over here and oxygen is shown negative. Is it possible? Again, it is incorrect, isn't it? It should have a positive charge. Look at this. You have this structure and in this, they are showing you the markings, how it is moving. It is moving from year to year, year to year, okay? So here they are telling you that the double bond is getting over here and you are getting a double bond over this and it's a single bond over there. Is it correct or incorrect? It is incorrect because from here the bond has got shifted. So it should, this carbon should have plus, that is missing. Also, you already have 2 hydrogens here. So if you go for the valency of the carbon, it is crossing more than 4 bonds. So therefore it is incorrect. Look at the last one. I hope you're all getting my points. Am I going fast? Hey, someone answer me. Am I going fast?
No, ma'am, it's fine.
See, I'm just showing you these basic examples so that you understand that when some resonance structures are there, asking you which is stable, which is not possible, all these things. So the moment you see these, you should be able to find it out. Just what are the things that you should look at it? The last one. They are showing you the shift from negative to this, fine, from year to year. From year to year. And they have given you some structure here. Is it possible? Definitely not. Why? Because where is the shift they are showing? They are showing the shift in a sigma bond. A sigma bond breakage is not possible. Only pi electron cloud disturbance is possible in resonance. So this is also incorrect. Okay. All these things are available in your Google Drive. So I'm just moving. Or do you want me to give time to copy these?
No, ma'am.
Okay, thank you. Going for major and minor resonance contributions. They'll be giving you which is major, which will contribute majorly to a molecule, which will be contributing minor to a molecule. Okay. So you have two resonance structures here. What is resonance structures? Resonance structures are the one when I start shifting my pi electronic cloud, whatever I get, that is resonance structure. Okay, here I have one negative. Again, here I have one negative. Yes, the conservation of charge is maintained. Fine. But which is majorly contributing, which is minorly contributing? That is the question. Which is majorly contributing, which is minorly contributing? What is the first thing? A carbon, generally carbon with negative is less stable with carbon with, okay, 1 minute. I'll take this case later. Okay. Fine. So look at this case, the first example A. What is it having? It is having a negative charge on the carbon. It is having a negative charge on the carbon and oxygen. And oxygen is present over there where it is not having any charge. Chargeless oxygen is present over here. There is no charge at all on oxygen. Look at the second example. In the second example, the carbon is not having any formal charge. Oxygen is having a negative charge. Comparing negative charge on carbon and oxygen, which is feasible, which is acceptable? Carbon or oxygen?
Oxygen.
Oxygen.
Oxygen. So when I compare these both are resonance structures only. I am not denying this can be available or this is not available. Both are available resonating structures only. But which is majorly contributing? When oxygen is having negative, that is possible. And therefore, this is allowed. This is major contribution. While this carbon that is having negative will be minor contribution. Okay. Going for the next condition. Look at here. This is CH3. Okay. CH3O, CH3, ether. So we have two molecules that is provided here, which is major and which is minor. Look at this. First of all, carbon is having positive here. Here, oxygen is having positive. Ma'am, oxygen is having positive, ma'am. So definitely it should be a minor. First thing that comes to our mind is that oxygen should not have positive, so it should be minor. Carbon with positive is okay. It's acceptable. But what is a major condition? The first condition is the number of covalent bonds, isn't it? Number of covalent bonds. Count the number of covalent bonds here it is having. Here it is 7 bonds and here it is 8 bonds. So more number of covalent bond is present over here, number 1. Number 2, what is the second condition? The carbon in organic chemistry, what is its necessity to keep on doing compounds? The only thing is that it should fulfill its octet. That is the reason it is going to form compounds. Here in this case, carbon did not fulfill the octet. But here case, the carbon has fulfilled its octet. Even to oxygen had a positive charge. These two conditions overwhelmed the third condition. Which two conditions? More number of covalent bonds and carbon has fulfilled its octet. Therefore, the second one is major and the first one is minor. Is that clear?
Yes, ma'am.
Thank you. Going for the next one. Ma'am, or there is resonance. Yeah, here 0 charges. Look at here, plus and minus will get cancelled. So again, it is 0 charges only. Acceptable. Which is stable? Which one is stable? Ma'am, carbon is having positive here. This is negative. We have 2 charges. Charge separation is also there. Yeah, charge separation is also there. So now, which is stable? Look at here. This is neutral molecule. This is neutral molecule. A neutral molecule is always a stable arrow. That's the first point. Also look at the number of bonds that it has made. 9 bonds. Here it is 8 bonds. So therefore, the first molecule is major and the second molecule is a minor one. Okay, so these kind of questions are quite common in resonance, asking you with respect to the stability and carboxylic acid stability. Just now we saw acetic acid, isn't it? Why is it stable? It's resonance stabilizing. What way? When the H plus is being released, what we have is this. So that involves a resonance between the lone pair of electrons and the pi electronic cloud. Therefore, carboxylic acid is resonance stabilized. So people will ask, carboxylic acid is a weak acid, but still it releases H plus. Why? See, we know carboxylic acid, when it releases COO minus, we say it is a strong conjugate base, isn't it? While the acid itself is a weak acid. Why it is a strong conjugate base? Because it is resonance stabilized. That is the reason. Okay, these kind of things are possible. And with respect to phenoxide, phenol is there when H plus is lost. And H plus is lost, it becomes phenoxide. It starts shifting its electrons. So resonance is stabilized there. There is no big charge separation that has happened. So therefore, you have a resonance stability in phenol. So these are the cases why phenoxide, phenol is acidic. Why phenol is acidic? Very, very common question. Why phenol is acidic? Phenol is acidic because it is resonance stabilized when it becomes phenoxide ion. That is the reason. All right. So that is with respect to your mesomeric and this effect. We will move on to steric hindrance where we have stopped in the last class. Hope you don't mind me moving just. You will be able to see it in the Google Drives. Am I correct?
Yes.
You'll be able to see it now.
Yes, ma'am.
Okay. Don't tell me, ma'am. I will not even open this and all after the class is over. Yeah, someone wanted to tell me something. Okay. Going for steric hindrance, what we saw in the last class. If you have a presence of bulky substituents, this generally decreases the reactivity. So look at cis-butene and trans-butene. Methyl groups are in the same phase and CH3 here are in the opposite plane. Okay. So its reactivity is more than cis. The reason is the two methyl groups being in the same plane. They are bulky enough. Therefore, the reactivity means someone is coming to approach it. Let me say some X is coming to approach it. It is very difficult to approach the alkene double bond because they are present over here. Okay. So this is called spatial crowding. Repulsion is there. So we will call this a steric hindrance or van der Waals strain. What are the things that may lead you to? Difficulty in approach by reagent. If a reagent is coming to approach it, it's very difficult. Electronic factor that prevents the electron availability at particular site. At a particular site, if a large electronic cloud is there, that will also be affected by this bulky substituents. So more is the steric strain. Ma'am, more strained, ma'am. In the last class, I told you, when you compare cyclopropane with cyclohexane, cyclopropane is more strained. So therefore, this is less stable. Go for this. You have carboxylic acid here. If I want to do some esterification reaction at this carboxylic acid, if I add two bulky groups at its ortho position, the reaction at COOH is very difficult. Look at this case. I have a trimethyl group that is present at this carbon, and I try to nitrate the benzene. Generally, methyl groups are electron donating groups which has plus I effect. Plus I effect always lead to orthopara directors. They direct the substituent to the orthopara position. So what should you expect? You expect nitro to be placed here, but where is nitro is done? Nitro is getting added in this para position, not at ortho. Why? Because it is sterically hindered. So many bulky groups are there. Going for this, haldehyde and ketone. Haldehyde is generally reactive than ketone. Why is the reason? Here only one R is there, but in ketone we have two R's are there. So sterically hindered. So therefore haldehyde reacts better than ketone. Going for the next one, which is more acidic. You know, electron withdrawing group increases the acidity. So nitro group is present in both the things. But still I have two methyl groups. In the last class, I told you this example. Two methyl groups are there. Methyl itself are electron donators. So when the nitro tries to pull its electron, the electronic shifts from this O to reach nitro is very difficult because two methyls are already there. So this can easily take up the electronic cloud from this so that it can release H+. So therefore, its acidity is more than this. What is deciding this? Steric hindrance is deciding it. Two methyl groups which are very quite close to nitro is lowering its acidity while this increases the acidity. Is that clear? Is that clear? Can we move on to the next topic?
Ma'am, could you explain the fifth point?
What, ma'am?
Fifth point.
Fifth point. This point.
Yes, ma'am.
Look at the molecule here. We have OH. The question is, which is more acidic? Which is more acidic is the question. Either this or this. Both the molecules are being substituted with the same molecule. 1 OH, 2 Me, and 1 NO2. Generally, electron withdrawing group is increasing its acidity. What is the electron withdrawing group here? Nitro is the electron withdrawing group here. Only 1 NO2 in both the cases. So we expect that both should be equally acidic. But this molecule is more acidic than this molecule. Why? What is the reason? See, nitro, as it is trying to pull the electron from this oxygen so that it will release it as H+, it will take up its negative charge. It will take up its electron, isn't it? What is acidity? Acidity is nothing but release of H+. So if it is releasing H+, what will happen to it? Its lone pair of electron will be intact with oxygen, so nitro can pull this electron. When will this happen? When will this happen? Only when nitro is able to pull up the electron strongly from this OH. Isn't it? Look at here. This is OH, which is connected with benzene. Only if the pull is very strong, what will happen? This oxygen will urge the H to get cleaved as H+, so that oxygen will have more electron to give for this benzene. When will this happen? When this pull is too high. When will this pull be too high? Nitro is there in both the cases, but only at para position it is present. Same positions only. But the methyl group that is present here in both the cases are different. Here it is very close to nitro. In the second case, sorry, it is far away from nitro. So nitro here feels steric hindrance from methyl group. It is not able to pull the electronic load from O. But here it is very free. The places are very free here. So therefore, the electron pull is easy for nitro. Clear, ma?
Clear.
We have hydrogen bonding. Let me complete it. Next one is hydrogen bonding. Very influential force with respect to organic chemistry. So what is this hydrogen bonding basically? First of all, what is the condition? Hydrogen should be bonded to electronegative atom. Look at this hydrogen. It is bonded to an electronegative atom. That is correct. So the more is the electronegativity. Ma'am, this is fluorine. Too much is its electronegativity. Therefore, the polarization becoming delta plus is also very, very high. Isn't it? So if an hydrogen is like that, which is bonded to an electronegative element, this hydrogen can go and bond with another electronegative element. This is called hydrogen bonding. I repeat once again. This hydrogen should be bonded with an electronegative atom. Because of the charge polarization, separation of charges, this hydrogen becomes more electropositive so that it bonds to an electronegative atom and another electronegative atom. This is called hydrogen bonding. The size of the atom should be very small. Which atom they are telling? This atom, to which it is going to get attracted. Its size should be also small. It should not be a bigger one. Like what to say, like iodine, like bromine. No, it should be also small. Then only the electrostatic attractive force will be large enough. Smaller size, more is the electrostatic attraction. So what kind of elements are generally being seen with hydrogen bonding? Fluorine, oxygen, nitrogen, all of them form hydrogen bonding. But what about in organic molecules, ma'am? Don't they form hydrogen bonding? Yes, they form. But not like very efficiently like this. The strength of the hydrogen bonding formed in an organic molecule is less compared to an inorganic one. Look at it. This hydrogen is bonded to carbon. But when you compare the electronegativity difference of carbon and hydrogen, they are not much different. They are very close enough. Carbon is little bit electronegative, but not much difference like your halogen. But still, hydrogen is electronegative. Hydrogen forms. Hydrogen is forming an delta plus charge. Now, with the chlorine that is available in carbon, they form an hydrogen bonding between them. Okay. So, hydrogen bonding happens in both inorganic molecule as well as in organic molecule. What is hydrogen bonding? And hydrogen is bonded to an electronegative atom. And because of the charge polarization, that hydrogen again gets bonded with another electronegative atom. That atom should be smaller in size. So what types of hydrogen bonding are there? Two types of hydrogen bonding are there. One is intermolecular, another is intramolecular. Two types are there. Inter means between two different molecules. Between different molecules. Chemistry, I don't know why people actually named it like this. If it was in the same way, it would be easily understandable. But here it is the opposite way. When I say intermural sports, it means between your school itself. Intramural sport means between the different schools. But in chemistry, it is different, opposite. Inter means between different molecules. Inter means within the same molecule. Is that clear, da? It is between the different molecules. Here it is within the same molecule. Okay. So if it is an intermolecular hydrogen bonding, that means what? With different molecules, the bonding has happened. So it can be between the same compounds or even between the different compounds. What does it mean, ma'am? See, if HF is there, if HF is making an hydrogen bonding with again an HF itself, this is also called as intermolecular only. Because why? This is one single compound. This is another separate compound. But they are the same compounds only. Same compound. Yes or no? Water. The water is having hydrogen bonding. Yes or no? Hello?
Yes, ma'am.
Yes, ma'am.
So here you are able to find this. Isn't it? Both are water only, but different. But as a molecule, it is one separate water molecule. It is another one separate water molecule. So this is also hydrogen bonding. Look at the second case, where the hydrogen bonding is happening between different compounds. Water is there. Hydrogen is bonded with an electronegative element oxygen when this is getting bonded with nitrogen. This is also hydrogen bonding. Water and ammonia, water and alcohol. This is also hydrogen bonding. In those cases, the boiling point increases. Whenever there is an intermolecular hydrogen bonding, that means what? The bonding that is happening between different moiety. It could be same moiety also, but different one. That means another one, repetitive one or a different one like this. HF or H2O ammonia. These cases, the boiling point increases. That means what? They are being captivated by the another molecule so that you have to give so much of heat for them to break the bond and get released as vapor state. Intramolecular, within the same compound. Look at this. Nitrophenol. I have oxygen which is bonded with nitrogen. I have hydrogen that is bonded with oxygen. They are forming an hydrogen within the same molecule. Therefore, it is very easy for you to boil it because within them they are very compact. They have made up themselves. So easily I can vaporize them. So the boiling point decreases. Most of the questions in mains level are with respect to hydrogen bonding. Ask me which is having more boiling point, more melting point, more solubility, all those stuffs. So what should you remember? If it is inter means what? Inter means between different molecules. The boiling point is more. If it is within the same molecule, intra, then it is having less boiling point. Okay. Dipole attraction. What are the effects of it? Dipole attraction is very strong. Yes or no? Yes. Dipole attraction here, delta plus delta minus, is very strong. Molecule becomes very polar. Molecule is becoming very polar, isn't it? Look at it. Phenol versus alcohol. Whose dipole moment is more? It's obvious its dipole moment is more. Why? This is so plus and this is so minus. But phenyl is not that much positive. It's not positive at all, isn't it? Therefore, dipole moment, with respect to dipole moment, alcohols are having more dipole moment compared to alkyl alcohols are having more dipole moment compared to aromatic alcohols. Going for the second case, boiling point. Look at this. Aldehydes or it could be ketone. Their boiling points are generally more than their corresponding hydrocarbon. What is this corresponding hydrocarbon here? If I'm telling CH3CHO, its corresponding hydrocarbon is C2H6. It's 2 carbons, isn't it? 2 carbons. So when you compare the boiling point, its boiling point will be more than this boiling point. Why? Because of the polarity that exists there. Look at this, carbon delta plus and O minus. Polarity is there. So therefore, it is boiling point is high. So we can say polarity is directly proportional to boiling point. Look at the second case here. Alcohol is there, ester is here. When I compare with, aldehyde and ester is there. When I compare with alcohol and ethanol and alcohol, again. So you have alcohol here, ester here you have acid and an alcohol. Whose boiling point is more? Its boiling point is more. Why? They are able to form an hydrogen bonding. Yes or no? Look at the structure of your aldehyde. Where is the hydrogen bonded to? It is bonded to carbon. That is not more electronegative. So if this hydrogen bonding goes for some hydrogen bonding, let me say with water, will it be having a strong hydrogen bonding? Or compare an acid or COOH. Here the hydrogen is bonded to oxygen, which is more electronegative. So if it goes for an hydrogen bonding, it will be stronger. Correct? Am I correct?
Yes, ma'am.
Okay. Going for the next one. Again, alcohol, when you compare with an hydrocarbon, alcohol has a proper, can form an intermolecular hydrogen bonding. We just now saw this is delta minus, this is delta plus. It can go for an intermolecular hydrogen bonding, isn't it? So therefore, alcohols have more boiling point compared to your corresponding hydrocarbon. Going for the next one, phenol versus alkyl halides. Here you have the possibility of forming hydrogen bonding. So therefore, its boiling point is more. So number one, you will be made to compare the molecules which has the possibility of forming hydrogen bonding and which do not have the possibility at all to form hydrogen bonding. Like this case, possibility is there. Or this case, where they form the hydrogen bonding with respect to their polarity changes, like whether it is the hydrogen is available with the electronegative group or less electronegative or more electronegative or this way. Whether it is forming an intermolecular hydrogen bonding or intramolecular hydrogen bonding. 3 types of questions are possible. Inter, the boiling point is more. Intra, the boiling point is less. Okay. Going for solubility. So with respect to solubility, what would we know? More is the non-polar group. NP means what? Non-polar. Non-polar group is more. They will become less soluble. Obviously, whenever I say that soluble, without telling you the solvent, ma'am, they didn't mention me the solvent at all. If the solvent is not mentioned, you should understand it is water. If they wanted to say some different solvent only, they will specify the solvent. If not, the solvent is water. Right? So here, when I talk about the solubility, water is a polar molecule. So like dissolves like, isn't it? Polar dissolves polar. When I look at the polarity, which is more polar, this or this, which is more polar? Obviously, alkyl alcohol is more polar, isn't it? This is delta plus and delta minus. Here it is also delta minus, partially delta minus. Sorry, there was a technical glitch here. I'm audible now?
Yes, ma'am.
Ma'am,
Okay.
Yes, ma'am.
So generally, those carboxylic acid with more than 7 carbons, okay, when it is going to be an octanoic acid, they are not soluble because they have more hydrocarbon part. So these kind of questions are quite common, very common. Yes. So what are the points that we should remember with respect to boiling? All of them are available under the electromeric and mesomeric effect in Google Drive. Those students who have joined new, please address the admin to join you in the WhatsApp group of class 11th. And students, if you have the Google Drive link that was shared to you, please, newcomers or those who have shifted from other batches, as from the old students, the Google Drive links that has been passed to them till now, so that you can see the notes there. Okay, going with boiling points and melting points. What are the common things that we should remember? So the liquid that can form hydrogen bonding generally has high melting point. So if it is a intermolecular hydrogen bonding, it is a increased boiling point, intra decreased boiling point. Linear chain, if it is a linear chain, the boiling point increases with its molecular mass. That means, ma'am, pentane's boiling point will be lesser than an octane. They are linear chain only, but as the molecular mass increases, van der Waals force of attraction increases, so boiling point increases. Branching, if it's a branched hydrocarbon, what happens? The boiling point decreases. Why? More surface area is available. See, for example, it's a pentane. Like this, it is a N-pentane. And I go for branching of it. If it is like this, what has happened? The surface area, that means all the part of them are able to take up the temperature. The more surface area is available right now, so that what happens? The boiling point is decreasing. So therefore, easily they will be able to vaporize. Liquids with van der Waals force and dipole-dipole moments have low boiling point. With respect to melting point, again, melting point and boiling point, you should remember if they have van der Waals or covalent bonding, their boiling point or melting point will be lower only. Going with acids with even number of carbon. Okay. If it is an acid with even number of carbon, if it is a trans isomer, if it is a symmetrical molecule, if it is a large molecule, in all these cases, melting point will be more. I repeat once again, if it is a compound with even number of carbon, if it is a compound which is a trans isomer, if it is a symmetrical, ma'am, trans means what? It is present like this. It is symmetrical, right? Center of symmetry it has. If I pass a line through its center, I'm able to cross both of this. Again, I'm able to pass both of them. They are symmetrical. So there, their melting point is more because they have a lot of interaction between them. If it's a large molecule, also melting point is more. So these are the concepts that we should remember with respect to hydrogen bonding. Is that clear, ma'am?
Yes, ma'am.
Okay. We will just start with stereoisomerism and we'll continue it in the next session. So what do we understand by stereoisomerism? First of all, whatever I'm going to say it in a 3D, three-dimensional way. Whatever we are going to say it in a three-dimensional way, I would say it is stereoisomerism, isn't it? I call this as stereoisomerism. So even when I say it's methane, you just draw like this. It's a 2D structure. It's a 2D, isn't it? But if I'm going to draw it in a 3D, I would show you that how are they really present? Like this, like this. One is above the plane, while the another one is below the plane. These are in the plane, isn't it? These hydrogens are in the plane. All these things has to be said. All these things has to be said. So this is three-dimensional structure. So in the case of stereoisomerism, there are various ways by which a molecule can be shown. We have wedge formula to projection. These are called projections. In case of projections, we have wedge formula is there. There is sawhorse formula. And you have Newman projection. You have Fisher projection. And by these ways, we will be able to show the same molecule in different ways, different perspectives of showing them. Okay, so we will see one of it now. Again, this is also available in Google Drive. So the first one is wedge dash formula in 3 dimensions. This is nothing but methane. So assuming this is carbon, and these are hydrogens. Are you able to see this? Yeah, this. They are almost in the plane only. But this, if I am the person who is standing here, this is coming towards me and this is going out of me. Yes or no? This is what I'm projecting here. C, this is D. They are in the plane. But what about this B? This is just pointedly coming towards me. So they will be generally showed by this kind of a wedge. This is called wedge. Wedge means what? A thick one, thick, broader one. This comes in front of me, while this is going back of me. So that will be shown as a dotted way or a dashed way. So Fisher projection, this is wedge formula. This is wedge dash formula or projection. Fisher projection. Ma'am, I am unable to do all these things. I am not able to show you this dash, wedge and all. But still I have to say people which is coming in front of me, which is going in back of me. All these things I should say. First of all, why should I say this? Because what we are learning right now is stereochemistry. Stereo means 3 dimension. On a blackboard, if we draw something, it is 2 dimension. A molecule's reactivity can be explained only with stereoisomerism. There are various chemical reactions. Whatever chemical reactions that we are learning right now, they are common chemical reactions. They are not stereo-specific. That means, see, for example, this is one hydrogen, which is back of it. And imagine this is not going to be hydrogen. Some molecule is there. Let us say it's CH3. This is CH triple bond CH. Something is there. If this CH3, if this CH triple bond CH is on the plane, then only one kind of reaction will happen. If I assume this was at the back of it, that kind of reaction would have not happened. So all these things can be explained only with stereochemistry. This is more complex chemistry, more advanced part of the chemistry. Okay. How do you explain how this reaction happened? When I added an alcohol, this is not reacting, but the other form was reacting, ma'am. It is because that part which was readily available for the reactant should be available for the reactant, isn't it? So those will be explained by stereochemistry. So for molecules with more number of carbon atoms, not just one, ma'am, we have 2 carbon atoms there. More are there, more carbons are there. See, the first one example we took was methane. Only 1 carbon here. If it is having more carbon, the chiral carbon will be at intersection, at the middle point is your chiral carbon. Look at here. So for that, we should understand what is chiral carbon or chirality. If a carbon is bonded with 4 different substituents, 4 different substituents. We call this as chiral carbon. We call it as chiral carbon. If it is not, we call it as achiral carbon. That's it. If it is there, we call it as chirality. If it is not, then we call it as achirality. Okay. Now look at this. This is the chiral carbon. Is this a chiral carbon? Yes. This is one group that is substituted here. This is another group. This is another group. This is another. 4 groups are different. 4 different groups. The vertical line. What is the which is the vertical line? This is my vertical line. As the longest carbon chain. This is the longest carbon chain. Here in this molecule, you have not more than that. For example, if it is CH2 and it goes on CH3, CH2, CH2, then that becomes the longest chain, isn't it? Here there is no other group. This is my longest chain where the functional group that contains highly oxidized carbon is present. I repeat once again. If you have some functional groups, then where will they be available in Fischer projection? Only in the vertical line. In the vertical line, the most oxidized one will be at the first position. Comparing carboxylic acid and alcohol, which is more oxidized, obviously carboxylic. What is oxidized? More oxygens. Let us make it in layman way. Carboxylic has 2 oxygens, so it is more oxidized. So that is in the first position, followed by your alcohol, CH2OH. So these two are actually away from the viewer. So how I start projecting in Fischer projection? Number 1, you have to fix your chiral center at the middle, at the intersection. Number 2, the vertical line will be having the longest carbon chain. Number 3, highest oxidized one will be at the first, followed by the lowest. Then what do you mean? It means that they are away from the projection, away from the viewer. That means they are below the plane of paper. If this is my paper that I have drawn you, carbon is at the intersection, carboxylic acid and CH2OH, they are with the dashed line. What is dashed line? Dashed line means it is away from the viewer. So yes, it is away from the viewer. And HOH is in the horizontal. Horizontal lines are towards the viewer, obviously above the plane of the paper. You understand till this?
Yes, ma'am.
Okay. So this is with respect to Fischer projection. How do you do it? Now let us go on. I think it's 4:01 already. Okay, we'll continue in our next session. What I tell you is that please take up the Google Drive notes, start studying, and with package, you can solve resonance problems also. So we have completed first part of GOC. We need still more 3 hours together to complete the isomerism part. So isomerism is going to be basically different projections, the 3 projections that I told you, their interconversions, and about symmetry operations. Also regarding the PPL, plane polarized light. How does it pass through? What is the angle of rotation? All those stuff. So we maximum need another 3 or 4 hours to complete it. Okay. So as you said that you will be okay for an online session in between, I'll be arranging for a one at after 7 o'clock, definitely. Okay.
Ma'am,
Tell me that.
will the notes be available on G Drive?
Everything is there on G Drive. Da.
Okay.
I think I have also posted you now G Drive link for GOC.
Yes, ma'am. No, wait, ma'am, I will check.
Ma'am, the electromagnetic and mesomeric effect PDF alone is not able to be found, ma'am.
It's not it?
I'm not
Yes,
able to
ma'am,
find
it's
that,
not
ma'am.
there.
Electromeric and mesomeric.
It's not there, ma'am.
Yes, ma'am.
Yes.
Everyone, but I'm able to see it in my drive. Okay, I will make it visible. I think I have not enabled that. I'll make it visible, okay?
Okay, ma'am.
Okay, ma'am.
Okay. Okay, thank you then.
Thank you, ma'am.
Bye.
Thank you, ma'am.
Thank you, ma'am.
Ma'am,
Thank you, ma'am.
ma'am, I have a doubt, ma'am.
Tell me, da.
In advanced archive, there is this one sum I have doubts. Shall I send a photo or?
Send, ma, send.